As darkness falls and the world around you grows quiet, look up. The night sky has been waiting for you, patient, eternal, unchanged for thousands of years. Tonight, let's drift together through the velvet darkness above, where every point of light tells a story older than memory itself. When you gaze upward on a clear night, you might see anywhere from 2,000 to 3,000 stars with your naked eye, depending on where you are. Each one is a distant sun, and together they paint the same celestial portrait that guided ancient sailors, inspired poets, and comforted our ancestors as they too lay beneath this cosmic blanket. You're seeing exactly what they saw, the same constellations, the same gentle glow, connecting you to every human who has ever paused to wonder at the night. But here's something beautiful, you're not just looking at the present moment. You're gazing into the past. The light from even the nearest stars takes years to reach your eyes. When you see Sirius, the brightest star in our night sky, shimmering like a diamond against the darkness, you're seeing light that left its surface 8.5 years ago. That photon began its journey before you made plans for tonight, before last week's worries, traveling silently through the void just to meet your eyes at this very moment. And that starlight, that precious, ancient light, has traveled so far just to be here with you now. Most stars you can see are between a few dozen and a few hundred light years away, meaning their light has been traveling through space since before your grandparents were born, perhaps even before entire generations of your family walked the earth. The universe sends you these gentle messengers from the deep past, little packets of electromagnetic energy that crossed unimaginable distances to land softly on your retina. The darkness between those stars isn't empty, though. It's filled with possibility, with space itself, so much space that if you could somehow collect all the stars in our galaxy and redistribute them evenly throughout its volume, each star would sit alone, separated from its nearest neighbor by millions upon millions of miles of silent, peaceful void. The night sky is mostly stillness, mostly rest, mostly the deep calm of space breathing between points of distant fire. Even the darkness you see is a kind of gift. That black velvet backdrop exists because the universe is so wonderfully vast that light from the most distant reaches simply hasn't had time to arrive yet. You're resting beneath a sky that is dark not because it's empty, but because it's so magnificently infinite that even light, traveling at 186,000 miles per second, cannot fill it all. The night embraces you in this cosmic shadow, this gentle reminder of how grand and how peaceful existence can be. So breathe slowly, and let your eyes adjust to the darkness, the way they've been designed to do for millennia. Feel yourself becoming part of this ancient ritual of watching, waiting, and wondering at the eternal night. As your eyes settle into the darkness, you might notice something curious. Among all those constant, twinkling stars, a few points of light shine steadily, without that gentle flicker. These are the planets, our neighbors in this cosmic neighborhood, and they've been wandering across the sky since long before humans had words to name them. The ancient Greeks called them planets, which simply means wanderers, because while the stars seemed fixed in their eternal patterns, these mysterious lights drifted slowly against the backdrop of constellations, night after night, following their own patient paths. They were puzzling, mesmerizing, different. And tonight, if you're lucky, you might see one or two of them keeping you company, Venus perhaps, gleaming like a brilliant lantern in the hours after sunset, or Jupiter, that steady, cream-colored beacon that outshines nearly everything except the moon. What those ancient observers didn't know, what makes this even more beautiful, is that planets don't twinkle like stars because they're so much closer to us. Stars twinkle because they're so distant they appear as single points of light, and Earth's turbulent atmosphere bends and shifts that tiny point as you watch. But planets are near enough that they appear as small disks to our atmosphere, even if our eyes can't quite resolve that detail. The light from different parts of that disk averages out, creating that calm, steady glow. It's the universe's way of saying, these worlds are your neighbors, not distant strangers. And what neighbors they are! Jupiter, that serene wanderer in our evening sky, is so large that 1,300 Earths could fit inside it. It's a gas giant with no solid surface to stand on, just layers upon layers of swirling clouds and storms descending into depths we can barely imagine, all spinning peacefully through the void. Somewhere in its atmosphere, the Great Red Spot continues its centuries-old rotation, a storm larger than our entire planet, raging silently in the darkness while you rest here, safe and small beneath your own sky. If you've ever looked up and seen a bright light that seems almost too brilliant to be a star, steady and radiant near the horizon just after sunset or before dawn, you've probably witnessed Venus. Our sister planet shines so brightly because it's wrapped in thick clouds that reflect sunlight like a cosmic mirror. Those clouds are made of sulfuric acid, swirling around a world where the surface temperature could melt lead, and yet from here, from your safe distance, Venus appears as nothing more than the gentlest, most beautiful evening star, a luminous pearl set in deepening twilight. The universe can be fierce and tender all at once. Even Mars, when it graces our night sky, offers its own quiet comfort. That rusty red wanderer glows with a warmth unlike any other planet, colored by iron oxide, common rust, covering its ancient surface. The same process that turns a forgotten bicycle orange has painted an entire world in shades of red and ochre. 4.5 billion years of cosmic chemistry, creating beauty on a planetary scale, just for you to glimpse as a tiny dot of colored light. These planets follow the ecliptic, that invisible path across the sky that marks the plane of our solar system. It's the same road the sun and moon travel, the same highway all the major planets cruise along in their orbital rhythms. If you trace a line from where the sun set to where it rose, you're drawing the ecliptic across your sky, and somewhere along that gentle arc, the wanderers make their patient journey, moving just slightly from night to night, so slowly you'd hardly notice unless you watched carefully over weeks and months. There's something deeply soothing about this. The planets have followed these paths for billions of years, and they'll continue long after we're gone, tracing the same celestial roads in perfect, mathematical harmony. No hurry, no urgency, just the slow, eternal dance of worlds in the darkness, each keeping its own time, each exactly where it needs to be. Rest in that knowledge. The universe has its rhythms, ancient and reliable, playing out above you as you drift towards sleep. And then, of course, there is the moon, our closest companion in all the cosmos, hanging in the darkness like a lantern left burning just for you. The moon is so familiar that we sometimes forget how extraordinary it is. It's been humanity's night light for as long as there have been humans to see it, and long, long before that. When dinosaurs walked the earth, they saw this same moon, though it hung slightly closer then, appearing just a bit larger in their ancient skies. When the first simple organisms emerged from primordial oceans, the moon was already there, pulling at the tides, stirring the waters, perhaps even helping to create the very rhythms that allowed life to flourish. Tonight, wherever the moon is in its cycle, it's showing you a face that's always the same. The moon is tidally locked with Earth, which means it rotates at exactly the same rate it orbits our planet. This perfect synchronization means the same side always faces us, the familiar pattern of dark Maria and bright highlands that humans have gazed upon for millennia. We've never seen the far side with our naked eyes, not once in all of human history. The moon keeps that half to itself, a gentle mystery, a reminder that even our most constant companion holds secrets. The light you see isn't the moon's own, of course. It's sunlight, reflected and softened, transformed from the harsh brilliance of our star into something gentler, cooler, more suited to dreams. Moonlight is second-hand sunshine, arriving at only about 1/millionth the intensity of direct sunlight, filtered through the moon's ancient, dusty surface. That surface is covered in regolith, a fine powder created by billions of years of meteorite impacts, each tiny collision grinding the rock a little finer, until the moon became covered in a layer of dust so soft that astronauts' boots sank into it, leaving footprints that remain there still, unchanged, in the airless silence. Those footprints from the Apollo missions, pressed into the lunar soil over 50 years ago, are still there right now, perfectly preserved. Without wind or rain to erode them, they'll remain for millions of years, long after every building on Earth has crumbled to dust. Those simple boot prints will still mark humanity's first steps on another world. It's a beautiful thought, our most temporary gestures, preserved in the most permanent way, on a world that orbits peacefully above you as you rest. The moon is gradually drifting away from us, moving about 1.5 inches farther from Earth each year. The same tidal forces that lock its face toward us are slowly pushing it outward, a consequence of the gravitational dance between our two worlds. Billions of years from now, the moon will appear smaller in the sky, its gentle pull on our oceans weaker, but for your lifetime and countless generations beyond, it will hang at nearly the same distance, rising and setting in its patient monthly rhythm, waxing and waning like a cosmic breath. When the moon is full, it rises just as the sun sets, as if the universe is ensuring we're never without light. When it's new, it travels across the daytime sky invisible to us, taking its rest while the sun holds court. And in between, it shows us every gradual shade of illumination, the delicate crescent, the half-lit quarter, the swelling gibbous, each phase a reminder that change happens slowly, gently, in perfect increments. Ancient peoples tracked time by the moon's phases. 29.5 days from new moon to new moon, a lunar month that gave us our very concept of month. 12 of these moon cycles don't quite equal a solar year, which is why calendars became complicated, why we needed to reconcile the moon's rhythm with the sun's. But for most of human history, the moon was our clock, our calendar, our way of marking the passage of time. Farmers planted by it. Lovers met beneath it. Travelers navigated by it. Even now, the moon influences us in ways both obvious and subtle. It pulls at Earth's oceans, creating the tides that rise and fall twice daily in response to its gravitational embrace. High tide occurs not just on the side of Earth facing the moon, but also on the opposite side, as if the planet itself is being gently stretched by the moon's pull, creating two bulges of water that sweep around the globe as we rotate. The ocean remembers the moon, responding to it even when it's hidden below the horizon. So rest beneath this ancient companion, this wanderer that never wanders far, this light that has guided countless souls through countless nights. The moon is there for you, as it has always been, as it always will be, marking time in the most patient way imaginable. On the darkest, clearest nights, far from city lights, Perhaps in the countryside or by the ocean, you might see something that looks like a faint, glowing cloud stretching across the entire sky. A pale river of light, flowing from horizon to horizon, so subtle you might wonder if your eyes are playing tricks on you. This is the Milky Way, and you're not looking at a cloud at all. You're looking at the edge of your own galaxy, seeing it from the inside. There's something profound about this. Every star you've ever seen with your naked eyes belongs to the Milky Way. Every constellation, every planet, every point of light in the night sky, they're all part of this one vast spiral of stars, and you're nestled within it, looking out at your cosmic home from your small, quiet corner. The Milky Way contains somewhere between 200 and 400 billion stars, though no one has counted them all, and likely no one ever will. It's a number so large it becomes almost meaningless, like trying to count grains of sand on every beach on Earth. And yet each one is a sun, perhaps with its own family of worlds. That pale glow you see stretching across the sky is actually the combined light of millions upon millions of stars too distant and too faint to see individually. They blur together into that soft, cosmic mist, like countless candles viewed from very far away. When you look toward the constellation Sagittarius, toward the thickest, brightest part of the Milky Way, you're looking toward the center of our galaxy, where stars crowd together more densely, where the ancient heart of this great spiral slowly turns. At the very center, hidden behind veils of dust and gas, lies something both terrifying and strangely peaceful, a supermassive black hole called Sagittarius A*, weighing as much as 4 million suns. It sits there in perfect darkness, the gravitational anchor around which our entire galaxy rotates. And yet, despite its immense power, despite its ability to trap even light itself, it's so far away, 26,000 light-years distant, that you're perfectly safe. It exerts no more pull on you than any other distant object, and it will remain there, silent and invisible, for billions upon billions of years, a dark heart beating at the center of our spiral home. Our sun, our own star, the source of warmth and light that makes life possible, is just one star among those hundreds of billions. It's located about 2/3 of the way out from the galactic center, in a quiet suburban region of the Milky Way, in what astronomers call the Orion Arm, a minor spiral arm, nothing special, nothing remarkable. We orbit the galactic center at about 515,000 miles per hour, which sounds terrifyingly fast until you realize that at this speed, it still takes our sun roughly 225 million years to complete a single orbit. The last time we were in this exact position in the galaxy, dinosaurs were just beginning to emerge on Earth. We're on a cosmic merry-go-round so vast that a single rotation spans entire epochs of geological time. And yet you feel none of this motion. You rest here, perfectly still in your perception, while the Earth spins, while it orbits the sun, while the sun carries you around the galaxy, while the galaxy itself moves through space. All this grand choreography happens in such perfect coordination that you experience only stillness, only peace, only the gentle presence of stars above. The Milky Way itself is moving too, drifting through space along with its neighbors in what's called the local group, a small cluster of galaxies bound together by gravity. Our nearest major galactic neighbor is Andromeda, another grand spiral of stars similar to our own, visible on dark nights as a faint smudge of light in the constellation that bears its name. Andromeda contains roughly 1 trillion stars, more than twice as many as the Milky Way, and it's heading toward us at about 68 miles per second. Before you worry, know this: Andromeda won't arrive for another 4 billion years. That collision, if you can call it that, will be the slowest, gentlest merger imaginable. The distances between stars are so vast that when these two galaxies interpenetrate, barely any stars will actually collide. They'll simply pass by one another like ghosts, slowly stirring into a new configuration, creating a larger galaxy that astronomers have already nicknamed Milkomeda. The Sun will likely be flung into a new orbit, Earth along with it, and the night sky will be transformed, filled with unfamiliar constellations and a much brighter galactic glow. But that's so far in the future that it's not worth losing a moment's sleep over. Tonight, Andromeda is still a distant neighbor, and the Milky Way still arches overhead in familiar patterns. This river of stars has guided travelers for millennia. Polynesian navigators crossed vast stretches of the Pacific Ocean using the Milky Way as a celestial roadmap. Some cultures saw it as a path for spirits, a bridge between worlds. Others imagine it as spilled milk from a goddess's breast, giving it the name we still use today. Everyone who looked up saw the same light, the same glowing band, and found their own meaning in it. Let yourself dissolve into that river now, imagining yourself as just another point of light among billions, your small consciousness part of something incomprehensibly vast and ancient, floating peacefully in the great spiral dance. You've probably noticed that stars twinkle, that gentle shimmer and dance of light that makes them seem almost alive, winking at you from across the vast darkness. But here's a beautiful secret: the stars themselves aren't actually twinkling at all. They're shining steadily, constant and true, sending out their light in an unwavering stream. It's our atmosphere that creates that shimmer, that soft fluctuation you see. As starlight passes through Earth's atmosphere, it travels through layers of air at different temperatures and densities, each one bending the light just slightly, like looking at a penny at the bottom of a rippling pool. The air is never perfectly still, it shifts and swirls with wind and temperature changes, especially high up where the atmosphere grows thin, and so the starlight bends this way and that, arriving at your eye along slightly different paths from moment to moment. The result is that gentle twinkle, that precious shimmer that has enchanted humans since we first looked upward. On nights when the atmosphere is particularly turbulent, stars twinkle more vigorously. On calm, stable nights, they shine more steadily. Astronomers actually prefer nights when stars don't twinkle much. They call it good seeing, because the steadier the starlight, the clearer their view through telescopes. But for those of us simply lying beneath the stars, there's something magical about that twinkle, something that makes the stars feel less like distant balls of plasma and more like friendly lights, acknowledging our gaze. The colors of stars tell stories too, though you need to look carefully to see them. Most stars appear white to our eyes, but if you observe closely, you'll notice subtle differences. Some stars have a slight blue-white tint, others lean toward yellow, and a few shine with a distinctly orange or even reddish hue. These colors reveal the star's temperatures, their inner fire made visible across impossible distances. Blue stars are the hottest, burning at temperatures of 30,000 degrees Celsius or more at their surface. They're massive, brilliant, and tragically short-lived by cosmic standards, blazing through their fuel in just a few million years. Red stars, by contrast, are cooler, though still thousands of degrees hot, and they can burn steadily for tens of billions of years, far longer than the current age of the universe. Our own sun sits comfortably in the middle, a yellow-white star with a surface temperature of about 5,500 degrees Celsius, neither too hot nor too cool, steady enough to have nurtured life on Earth for billions of years and steady enough to continue for billions more. When you look at Betelgeuse in the constellation Orion, that distinctive reddish star marking the hunter's shoulder, you're seeing a red supergiant nearing the end of its life. It's already burned through most of its fuel and swollen to an enormous size. If you could place Betelgeuse where our Sun is, its surface would extend past the orbit of Mars, engulfing Mercury, Venus, Earth, and the red planet entirely. And yet from here, from your safe distance of about 650 light-years away, it's just a beautiful red, twinkling peacefully among its neighbors. Betelgeuse could explode as a supernova at any time, tomorrow, or 100,000 years from now, and when it does, it will briefly shine as bright as the full moon in our night sky, visible even in daylight. But at any time in cosmic terms is different from human time. It's been getting ready to explode for millennia, and it might continue preparing for millennia more. There's no urgency in the universe, no rushing. Even stellar death happens on its own schedule, in its own time, and we simply wait and watch. Look toward Rigel, the blue-white star at Orion's foot, and you're seeing the opposite extreme, a young, hot star pouring out tremendous energy, living fast and bright. It's roughly 40,000 times more luminous than our Sun, but because it's burning so fiercely, it will exhaust itself relatively quickly. These blue giants are the brilliant shooting stars of the cosmic timescale, spectacular but brief. Between these extremes lie countless other stars, each with its own temperature, its own color, its own story of birth and life among the clouds of gas and dust that drift through the galaxy. Some are solitary like our Sun. Others exist in pairs or even larger groups, locked in gravitational dances, orbiting around common centers of mass and rhythms that span years or centuries. Many of the stars you see are actually double stars, two suns orbiting each other, so close together they appear as one point of light to your naked eye. Albireo, in the constellation Cygnus the Swan, is one of the most beautiful examples. Through even a small telescope, it reveals itself as a stunning pair, one golden yellow, one sapphire blue, like cosmic jewels set side by side. They've been orbiting each other for billions of years, two different temperatures, two different colors, bound together by gravity's gentle insistence. There's something comforting in knowing that stars come in pairs, that even in the vastness of space, things find companions, find partners, find others to dance with through the long ages of time. You're never truly alone in the universe, everything is connected to something else, held by forces both visible and invisible, all part of the same grand tapestry. So as you watch the stars twinkle and shimmer, remember, you're seeing them through the veil of your own atmosphere, through the protective blanket of air that makes life possible on this world. Each shimmer is a reminder that you're home, safe beneath layers of nitrogen and oxygen, watching distant fires that have burned steadily long before you were born and will burn long after, their light crossing the void just to dance for you, just for this moment. For thousands of years, humans have looked up at the night sky and seen not just individual stars, but patterns, pictures drawn in light, stories told across the darkness. These are the constellations, and they're one of humanity's oldest forms of storytelling, a way of making sense of the vast and overwhelming night by filling it with familiar shapes and ancient myths. The constellations you see tonight are the same ones that guided shepherds in ancient Mesopotamia, that helped Egyptian priests mark the seasons, that inspired Greek poets to weave tales of heroes and monsters. Orion the hunter still stalks across the winter sky, his belt of 3 bright stars unmistakable even to the most casual observer. Ursa Major, the Great Bear, still circles the north celestial pole, its 7 brightest stars forming the pattern we call the Big Dipper, pointing eternally toward Polaris, the North Star. But here's something wonderful to remember: the constellations aren't real in the way we imagine them. The stars that form Orion, for instance, aren't actually close to each other in space. Betelgeuse, marking his shoulder, is about 650 light-years away, while Rigel at his foot is roughly 860 light-years distant. Bellatrix, another bright star in Orion, sits about 250 light-years from Earth. These stars only appear to form a pattern because of our particular viewing angle, our specific position in space. If you could travel to another star system and look back, the constellations would be completely unrecognizable, scattered into new and unfamiliar configurations. We're seeing a cosmic coincidence, a alignment of stars that happens to create meaningful shapes only from Earth, only from here, only for us. It's a reminder that perspective matters, that beauty often exists in the eye of the beholder, that meaning can be found even in randomness when viewed from just the right angle. Different cultures saw different patterns in the same stars. Where the Greeks saw Ursa Major as a great bear, Native American tribes saw a bear being chased by hunters. The ancient Chinese saw it as part of the purple forbidden enclosure, associated with the celestial palace of the emperor. The same 7 stars, the same light, but different stories, different meanings, each culture writing its own narrative across the universal canvas of the night sky. The spaces between the stars seem empty, just darkness, just void, but they're actually filled with something subtle and beautiful. Thin clouds of gas and dust drift through the galaxy, so tenuous that even the best vacuum we can create on Earth is dense by comparison. These are the nebulae, and they're the birthplaces and graveyards of stars, the cosmic gardens where light is both born and returns to rest. Some nebulae glow with soft colors, pinks and reds and blues, lit up by the radiation from nearby stars. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one of these glowing stellar nurseries. It's a vast cloud of hydrogen gas, illuminated from within by newborn stars, so young they're still surrounded by the material from which they formed. Right now, as you rest here, new stars are being born in that nebula, condensing out of the gas and dust, gathering mass, growing warmer, moving toward that critical moment when their cores become hot and dense enough to begin nuclear fusion and they ignite, becoming stars in their own right. This process takes millions of years of slow gravitational collapse, of gas falling inward, of density and temperature gradually increasing in the dark. And yet somewhere in the Orion Nebula, perhaps in a region we can't even see clearly through all the dust, a star might be on the verge of igniting right now, about to join the community of light that fills the galaxy. Birth happens even in the depths of space, though with patience that makes our fastest processes seem frantic by comparison. Other nebulae are the remnants of stars that have died. When a star like our Sun exhausts its fuel, it gently puffs off its outer layers into space, creating what's called a planetary nebula, though it has nothing to do with planets. The name comes from early astronomers who thought these round, fuzzy objects looked like distant planets through their small telescopes. These expanding shells of gas, lit from within by the dying star's remaining core, create some of the most beautiful structures in the night sky. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, each one is a star's final breath, exhaled into the cosmos in slow, luminous rings. These nebulae glow for thousands of years before fading, gradually dispersing into the space between stars, their atoms mixing with the general interstellar medium, becoming available for future generations of stars and planets. The oxygen you're breathing right now, the carbon in your body, the iron in your blood, all of it was forged inside stars that died billions of years ago, stars that ended their lives by returning their enriched material to space through gentle planetary nebulae or more violent supernova explosions. You are, quite literally, made of stardust. This isn't poetic metaphor, it's established scientific fact. Every atom in your body heavier than hydrogen was created in the heart of a star, cooked in nuclear furnaces operating at millions of degrees, then scattered into space when those stars died. Your body is a collection of recycled stellar material, temporarily organized into the pattern of a living, breathing human being, currently resting beneath the very stars whose ancient deaths made your existence possible. The zodiac constellations, those 12 patterns the sun appears to pass through over the course of a year, have captivated humans for millennia. Aries, Taurus, Gemini, Cancer, and the rest mark out the ecliptic, that same path we mentioned earlier where the planets wander. Ancient Babylonians identified these patterns over 3,000 years ago, using them to track the seasons, to know when to plant and when to harvest. The stars became a calendar, a cosmic clock marking the year's passage with reliable precision. When the sun is in Taurus, for instance, you can't actually see Taurus in the night sky, it's up during the day, lost in the sun's glare. But 6 months later, when the sun is moved to the opposite side of the ecliptic, Taurus rises in the darkness, visible all night long. The constellations play hide and seek with the seasons, each taking its turn in the spotlight of night, each waiting patiently for its moment to shine. Some constellations are circumpolar, meaning they never set below the horizon if you're viewing from certain latitudes. If you live in the northern hemisphere, Ursa Major and Cassiopeia circle around Polaris continuously, visible every night of the year, eternal companions in the sky. They will around the north celestial pole like patient sentinels, marking the hours as Earth rotates, rising and falling but never disappearing entirely. Polaris itself, the North Star, has guided countless travelers throughout history. It sits almost directly above Earth's North Pole, so it appears nearly stationary while all the other stars wheel around it. If you're lost in the wilderness and can find Polaris, you've found true north, an anchor point in the confusing darkness. Ancient sailors navigated by it. Escaping slaves followed it northward to freedom. It's been a beacon of hope and direction for as long as humans have wandered beneath the stars. But even Polaris won't be the North Star forever. Earth's axis wobbles very slowly over time, a motion called precession, completing one full cycle every 26,000 years. This means that different stars take turns being the pole star over these long cycles. 5,000 years ago, when the ancient Egyptians were building the pyramids, the star Thuban in the constellation Draco was the North Star. 13,000 years from now, the bright star Vega will have that honor. The sky itself changes, though so slowly that 100 human lifetimes wouldn't notice the difference. The stars and constellations are also moving, drifting through space at different speeds and in different directions, though they're so far away that their motion is imperceptible to us. The Big Dipper you see tonight looks essentially identical to the Big Dipper seen by Julius Caesar, by Cleopatra, by the builders of Stonehenge. But if you could watch over hundreds of thousands of years, you'd see it slowly distort and change shape, the stars drifting apart, the familiar pattern dissolving into something new and unrecognizable. Even the constellations are temporary, though they last for many, many human epochs. For now, though, they remain our companions, our familiar friends in the night. They mark the seasons for us just as they did for our ancestors. They help us orient ourselves in space and time. They give us stories to tell, patterns to recognize, a sense of order in the overwhelming vastness. When you look up and recognize Orion or the Big Dipper, you're participating in one of humanity's oldest traditions, the simple act of finding shapes in starlight, of making the infinite feel just a little bit more knowable, more friendly, more like home. So rest beneath these ancient patterns, these stories written in light across billions of miles of space, and know that you're part of a long chain of stargazers stretching back to the very beginning of human consciousness, all of us looking up, all of us wondering, all of us finding comfort in the same gentle lights. The dust between the stars, so fine that millions of particles would fit on the head of a pin, also plays a crucial role in the cosmic story. This dust absorbs and scatters starlight, sometimes obscuring our view of distant parts of the galaxy. The dark patches you see in the Milky Way, those regions where the glow seems to dim or disappear, aren't empty voids. They're dense clouds of dust blocking the light from stars beyond, creating what look like dark rivers or rifts in the luminous band of the galaxy. But this dust isn't just an obstacle to our vision. It's also the material from which planets form. When a new star is born from a collapsing gas cloud, not all the material falls into the star itself. Some remains in orbit, forming a disk of gas and dust around the young star. Within this disk, dust grains slowly collide and stick together, growing from microscopic particles to pebbles to boulders to planetesimals to, eventually, planets. Earth itself began as countless tiny dust grains in orbit around the young sun, 4.5 billion years ago, gradually accumulating into the world you now rest upon. Those same processes are happening right now around young stars throughout the galaxy. Planets are forming, growing from dust, developing their own characteristics, perhaps even creating conditions where life might someday emerge. The universe is constantly creating new worlds, new possibilities, new chances for matter to organize itself into interesting patterns. It never stops, never rests, never runs out of creativity. Some of these dust clouds are so dense and so dark that they can be seen as silhouettes against the brighter background of the Milky Way. The Coalsack Nebula, visible from the southern hemisphere, appears as a dark void near the Southern Cross, a patch of sky that seems to have no stars at all. But it's not empty. It's full of cold gas and dust, waiting, perhaps, to collapse under its own gravity and begin forming new stars, continuing the cycle of birth and death and rebirth that has shaped the galaxy for billions of years. Even the space that seems truly empty, the vast gulfs between these clouds and nebulae, contains a few stray hydrogen atoms, roughly 1 atom per cubic centimeter on average. It seems like nothing, and by earthly standards it is nothing, but across the immense volumes of interstellar space, even this thin distribution adds up to enormous mass. The space between stars contains more mass than all the stars combined, though it's spread so thinly that you could travel through it without noticing anything at all. This is the medium through which starlight travels to reach you, crossing light years of near-perfect vacuum, passing through occasional wisps of gas and dust, journeying for years or decades or centuries before finally arriving at your eye. And somehow, despite all that distance, despite all those obstacles, the light makes it through, carrying information about the star that emitted it, preserving its color and intensity across the void, delivering its message to anyone patient enough to look up and receive it. So when you gaze at the stars tonight, remember that you're not looking through empty space. You're looking through a subtle, pervasive medium of gas and dust, the raw material of future stars and planets, the recycled atoms of stars long dead, all of it drifting slowly through the galaxy in currents and eddies and flows we're only beginning to understand. The space between the stars is as alive and dynamic as the stars themselves, just quieter, more patient, content to work on timescales that make even stellar lifetimes seem brief. The night sky itself is a gift of geometry and motion, created by the simple fact that Earth rotates. Right now, as you rest here in darkness, half the planet is bathed in sunlight, experiencing afternoon or morning or midday brilliance. They can't see the stars, not because the stars aren't there, but because the sun's light overwhelms them, flooding the sky with scattered blue light that drowns out everything else. But the stars are still shining, still sending their light toward Earth, patiently waiting for darkness to make them visible again. Earth rotates once every 24 hours, spinning from west to east, which is why the sun appears to rise in the east and set in the west, and why the stars seem to wheel across the sky in the opposite direction of Earth's actual rotation. You're not watching the stars move, you're feeling the Earth turn beneath you, though the motion is so smooth and constant you perceive only stillness. You're riding on the surface of a sphere spinning at roughly 1,000 miles per hour at the equator, and yet you feel no wind, no motion, no hint of this tremendous speed. This rotation creates the rhythm of day and night that has governed life on Earth for billions of years. Before there were eyes to see the sunrise, before there were minds to contemplate the stars, this rhythm existed, light and dark, regular as a heartbeat, reliable as breath. The earliest single-celled organisms evolved circadian rhythms matching this 24-hour cycle, internal clocks that helped them anticipate the coming of day and night. Those same cellular mechanisms exist in you now, ancient timekeepers inherited from ancestors so distant they barely resembled anything we'd recognize as life. But the day hasn't always been 24 hours long. When Earth first formed, it rotated much faster. A day lasted perhaps only 6 hours. The moon, much closer then than it is now, exerted stronger tidal forces on Earth's oceans and even on the solid rock of the planet itself, creating friction that gradually slowed Earth's rotation over billions of years. The moon stole Earth's angular momentum through this tidal interaction, which is why it's slowly drifting away from us, and why our days are slowly, imperceptibly getting longer, about 1.7 milliseconds per century. Billions of years ago, Earth's ancient organisms experienced shorter days and longer months, living under a larger moon that loomed dramatically in their skies. The creatures of the Devonian period, swimming in shallow seas 400 million years ago, knew days that lasted only about 22 hours. By the time of the dinosaurs, a day was perhaps 23 hours long. The universe operates on such fast timescales that even something as fundamental as the length of a day is fluid, changing, gradually stretching out over the ages. Billions of years from now, if Earth survives that long, days might last 50 hours, or 100, or more. Eventually, Earth might become tidally locked to the moon just as the moon is locked to Earth, with one side perpetually facing the moon, one hemisphere experiencing endless day while the other knows only night, and the stars visible only from that dark half of the world. But that's so far in the future that it exists only as a mathematical possibility, not something worth worrying about on this particular night, under this particular sky. The tilt of Earth's axis, that 23.5-degree angle relative to the plane of our orbit around the Sun, creates the seasons and also determines which stars you can see throughout the year. In summer, when your hemisphere tilts toward the Sun, you experience long days and short nights, and the nighttime sky shows you different constellations than you see in winter. Scorpius rises high in the summer sky, but in winter it's below the horizon, lost to your view, while Orion claims the night instead. This axial tilt means that someone at the equator experiences roughly 12 hours of day and 12 hours of night year-round, a balanced rhythm where darkness and light share time equally. But if you live far to the north or south, you experience wild variations, long summer days where the sun barely sets, followed by long winter nights where it barely rises. At the poles, this reaches its extreme, 6 months of continuous daylight followed by 6 months of continuous night. Half a year to watch the stars whirl slowly around the sky without the sun ever interrupting to chase them away. Imagine living through a polar winter night, months of darkness, stars visible at all hours, the moon cycling through its phases over and over without a sunrise to mark the passage of days. It sounds harsh, and in many ways it is, but there's also something magnificent about it, something that connects you to the cosmos in a way that daily sunrises and sunsets don't quite allow. You'd see the stars drift slowly westward as Earth orbits the Sun, watching the constellations change positions not because of Earth's rotation but because of its revolution, tracking the year's passage by which stars are visible rather than by the Sun's position. Even here, wherever you are, you can observe this same phenomenon if you watch the stars over weeks and months. A star that rises at midnight tonight will rise at 11 p.m. a month from now, and at 10 p.m. 2 months from now, gradually shifting earlier and earlier until, 6 months later, it's a daytime star, invisible in the sun's glare. The night sky is a slowly changing stage, with different constellations taking their turns in the spotlight as Earth makes its annual journey around the Sun. This orbital motion, Earth traveling around the Sun at about 67,000 miles per hour, is why we experience a year, why the seasons change, why the stars shift their positions gradually over months. You're not only spinning on the surface of a rotating planet, you're also hurtling through space on an elliptical path, though again, the motion is so smooth you feel nothing at all. The Sun's gravity holds you in this orbit, keeps Earth from flying off into the void, provides the centripetal force that maintains your circular journey through the darkness. And here's something beautiful to contemplate. Right now, at this very moment, you can imagine the Earth as a sphere hanging in space, half illuminated by the sun, half draped in shadow. The line between day and night, called the terminator, sweeps across the planet's surface as Earth rotates, bringing sunset to some places, sunrise to others, marking the boundary between the world that can see stars and the world that cannot. You're on the night side of that line, in Earth's shadow, gifted with darkness and therefore with stars. Somewhere on the other side of the planet, people are experiencing noon, the sun directly overhead, the stars completely invisible. In a few hours, as Earth continues its rotation, they'll cross into shadow and begin their own journey into night, while you'll eventually spin back into daylight. This exchange happens continuously, endlessly, a planetary dance of light and shadow that has continued for 4.5 billion years and will continue for billions more. So rest in this darkness, this temporary shadow, this gift of geometry that lets you see the stars. You're exactly where you need to be, at exactly the right time, on exactly the right part of Earth's surface to witness this particular view of the cosmos. The universe has arranged itself, through rotation and revolution, through tilt and orbit, to give you this moment of starlight. If you're patient enough, if you watch the sky long enough, you'll eventually see something magical, a streak of light suddenly appearing, racing across the darkness for just a second or two before vanishing completely. A shooting star, though it's not a star at all. It's a meteor, a tiny piece of cosmic dust or rock burning up in Earth's atmosphere, ending its billion-year journey through space in one brief, brilliant flash. These meteors are surprisingly small. Most are no larger than a grain of sand, some no bigger than the period at the end of this sentence. They've been drifting through the solar system for eons, fragments left behind by comets or asteroids, following their own orbits around the sun in patient silence. Then, by chance, their path intersects with Earth's path, and suddenly they're falling through our atmosphere at speeds of 45,000 miles per hour or more, their tremendous velocity converting to heat through friction with the air molecules. At that speed, the meteor's surface temperature reaches thousands of degrees. The air itself becomes so hot it glows, creating a brilliant streak of plasma, ionized gas, that traces the meteor's path across the sky. Most meteors burn up completely at altitudes of 50 to 70 miles above Earth's surface, never reaching the ground, simply vaporizing into atoms that drift slowly down through the atmosphere to eventually settle on the surface as cosmic dust. You've probably breathed in atoms from ancient meteors, particles that once traveled through interplanetary space before falling to Earth and becoming part of the air you breathe. Every day, about 100 tons of cosmic dust and small meteors fall to Earth. That's roughly the mass of a blue whale, arriving from space every single day, silently adding to our planet's mass one tiny particle at a time. Most of this happens in daylight or over the oceans, unseen by human eyes, but on any given night, if you're watching, you might see a few dozen meteors per hour under dark skies, evidence of this constant, gentle rain of material from space. Several times each year, Earth passes through the debris streams left behind by comets, creating meteor showers. The Perseids in August, the Geminids in December, the Leonids in November. These showers occur when Earth plows through regions of space dense with cometary particles, all traveling in roughly the same direction. During a meteor shower, you might see dozens or even hundreds of meteors per hour, all appearing to radiate from a single point in the sky. The shower's radiant, though they're actually on parallel paths, an effect of perspective like how parallel railroad tracks appear to converge in the distance. These meteor showers happen at the same time every year because Earth encounters these debris streams at the same point in its orbit annually. The Perseids occur every August because that's when Earth crosses the orbital path of Comet Swift-Tuttle, a massive comet that passes through the inner solar system once every 133 years, leaving behind a trail of dust and ice particles that spread out along its orbit. When Earth intersects this trail, we see the result as dozens of meteors per hour, all appearing to come from the constellation Perseus, ancient fragments of a comet, lighting up our atmosphere, giving us their final gift of light before vanishing forever. Very rarely, a meteor is large enough and strong enough to survive its fiery passage through the atmosphere and reach the ground. These are meteorites, and they're precious messengers from the early solar system. Most meteorites are pieces of asteroids, fragments broken off by ancient collisions, containing material that has remained essentially unchanged since the solar system formed 4.5 billion years ago. When scientists study meteorites, they're holding pieces of the primordial solar system in their hands, reading the history written in ancient minerals and crystal structures. Some meteorites contain tiny diamonds, formed billions of years ago in the atmospheres of dying stars and incorporated into the dust cloud that eventually became our solar system. Some contain amino acids and other organic molecules, suggesting that the building blocks of life might have been delivered to Earth from space. Others are fragments of the Moon or even Mars, blasted off those worlds by asteroid impacts and eventually falling to Earth after millions of years drifting through space. You can literally hold a piece of Mars in your hand, thanks to these chance deliveries from the cosmos. The largest meteorite ever found on Earth, the Hoba meteorite in Namibia, weighs about 60 tons and consists mostly of iron and nickel, forged in the core of a long-dead star. It sits where it fell, too heavy to move, a silent testament to the day it arrived from space with such tremendous energy that the impact should have created a crater. But it apparently hit at just the right angle and speed to slow down in the atmosphere enough that it landed relatively gently, settling into the ground without exploding, without vaporizing, just coming to rest after its journey. Most meteors you see tonight won't reach the ground. They'll simply give their light and disappear, their atoms dispersing into the atmosphere, becoming part of Earth in the most gradual way imaginable. But each one is special, each streak of light represents a genuine visitor from space, something that has traveled vast distances, existed for billions of years, and chose this moment, this place, to make its presence known before returning to cosmic dust. There's an old tradition of making wishes on shooting stars, and while these meteors have no power to grant wishes, there's something appropriate about the practice. A meteor's appearance is unpredictable, fleeting, and beautiful, much like the moments of grace and possibility that appear in our own lives. They remind us that the universe is dynamic, that things happen, that even in the vast stillness of space there are moments of sudden change and transformation. They're small miracles, occurring dozens of times per hour somewhere in Earth's atmosphere, waiting for patient observers to notice them and wonder. So keep your eyes on the sky tonight, and if you're lucky, you'll see one, a streak of ancient light, a cosmic farewell, a tiny fragment of the universe saying goodbye in the most luminous way possible. And in that moment, you'll be witnessing something that has traveled farther and existed longer than you can fully comprehend, all to burn brightly for you, just for you, in this particular stretch of darkness. One of the most profound aspects of the night sky is something you can't directly perceive, but it's there nonetheless, shaping everything you see. The space between you and the stars is almost perfectly silent. If you could somehow float out there among the stars, you would hear nothing, no sound of stellar winds, no roar of exploding supernovae, no hum of cosmic radiation. Just absolute, complete silence. Sound requires a medium to travel through, air molecules bumping into each other, transmitting vibrations from source to ear. But space is a vacuum so complete that there aren't enough particles to carry sound waves. Those 100 billion stars in our galaxy are all utterly silent from our perspective, their light reaching us but their sound forever lost to the void. Even the Sun, that roiling ball of nuclear fusion just 93 million miles away, makes no sound that reaches us across the vacuum of space. Scientists have estimated that if sound could travel through space, the Sun would produce a roar of about 100 decibels here on Earth, roughly as loud as a jackhammer, constantly, day and night, never stopping. We'd never experience true silence. But the vacuum protects us, gives us this gift of quiet, allows us to rest in peaceful darkness while the universe burns and explodes and churns in perfect, inaudible silence. The vacuum of space is profound in other ways too. The pressure at sea level on Earth is about 14.7 pounds per square inch, created by the weight of all the atmosphere above you. In space, the pressure is essentially zero. If you could take a jar of Earth's atmosphere and release it in space, it would immediately expand and disperse, the molecules flying apart from each other, spreading out until they were so far apart they might never collide again. The vacuum is patient and persistent, always ready to pull things apart, to separate, to create distance and emptiness. And yet, paradoxically, space isn't truly empty. Even in the vast gulfs between stars, there are occasional atoms drifting, mostly hydrogen, the simplest and most abundant element in the universe. About 1 atom per cubic centimeter, as we mentioned before, which sounds like nothing and almost is nothing. For comparison, the air you're breathing contains about 10 million trillion molecules per cubic centimeter. Space is empty in a way we can barely comprehend, a vacuum more complete than anything we can create on Earth, despite our best efforts. This emptiness creates a kind of purity. A photon leaving a distant star can travel for hundreds or thousands of years through space, encountering almost nothing. It doesn't scatter or slow down or change direction unless it happens to encounter one of those rare stray atoms or dust particles. It simply travels at the speed of light through the void, preserving the information about the star that created it, arriving at your eye essentially unchanged from the moment it was emitted. The vacuum preserves the light, keeps it pure, allows it to tell its story across vast distances. The cold of space is equally profound. Temperature, in a sense, is just the motion of molecules. The faster they vibrate and move, the hotter something is. But in the near vacuum of space, there are so few molecules that temperature becomes almost meaningless. The cosmic background temperature of the universe is about 2.7 degrees above absolute zero, roughly negative 270 degrees Celsius, the residual heat left over from the Big Bang itself, still radiating through space after nearly 14 billion years. This ancient warmth is everywhere, a faint whisper of microwave radiation filling the entire universe, the echo of creation itself. You can't see it or feel it, but it's there, washing over you right now, a reminder that even the emptiest parts of space contain traces of the universe's history. This cosmic microwave background radiation is the oldest light we can detect, released when the universe was only 380,000 years old, when it first became transparent enough for light to travel freely through space. The night sky you see is layered with different kinds of light from different eras. The stars are relatively recent by cosmic standards, their light left them years or decades or centuries ago. The light from distant galaxies, invisible to your naked eye but captured by powerful telescopes, might have traveled for millions or even billions of years before arriving here. And pervading everything, invisible to our eyes but detectable with the right instruments, is that ancient microwave glow, the afterglow of creation itself, the oldest light in the universe. Space is also filled with invisible fields, gravity wells created by massive objects, magnetic fields spiraling around stars and planets, the subtle quantum fields that permeate reality itself. These fields are active and real, shaping the behavior of matter and energy, even though you can't see or feel them directly. The very fabric of spacetime is curved by mass and energy, creating the invisible architecture that governs how planets orbit stars, how stars orbit the galactic center, how light bends around massive objects. And threaded through all of this is dark matter, a mysterious substance that makes up about 85% of all the matter in the universe but doesn't interact with light at all. We know it's there because we can see its gravitational effects. Galaxies rotate faster than they should based on their visible matter alone. Clusters of galaxies are held together by more mass than we can see. Dark matter creates an invisible scaffolding throughout the universe, holding things together in ways we're only beginning to understand. You're surrounded by it right now, dark matter particles potentially passing through your body constantly, interacting with normal matter only through gravity, silent and invisible passengers in the cosmic story. Even more mysterious is dark energy, a force that seems to be accelerating the expansion of the universe itself. Distant galaxies are moving away from us faster and faster, pushed apart by this strange energy that pervades all of space, a kind of anti-gravity that operates on the largest scales imaginable. About 68% of the universe's total energy is in this dark form, and we don't really know what it is or why it exists. The universe holds more mysteries than answers, more questions than certainty. But despite all these invisible components, despite the darkness and the cold and the silence and the vacuum, space is not hostile. It simply is. It exists in a state of profound neutrality, neither welcoming nor rejecting, just maintaining its laws with perfect consistency. Light travels at exactly the same speed everywhere. Gravity follows the same equations in every galaxy. The fundamental constants of nature remain constant across billions of light-years of space and billions of years of time. This reliability, this unchanging nature of physical law, is what allows stars to shine steadily for billions of years. It's what makes the orbits of planets predictable. It's what ensures that photons leaving distant stars will arrive at your eye carrying accurate information about their source. The universe plays fair, following its own rules without exception, creating a cosmos that is comprehensible, studyable, knowable, at least in principle. So as you rest beneath the stars tonight, remember that you're protected from the vacuum and the cold and the silence by your thin blanket of atmosphere, your protective cocoon that makes life possible. You're looking out at a realm of profound emptiness, profound quiet, profound stillness, and finding beauty in it, in the light that crosses that void, in the patterns that appear despite the distances, in the simple fact that anything exists at all rather than nothing. The silence of space is a kind of peace, the ultimate quiet, the deepest possible rest. And from here, safe and warm, you can contemplate it without fear, can let it soothe you, can allow the vastness and emptiness to put your own concerns into perspective. Whatever worries you carried into this night, they exist on a tiny, warm, noisy planet, while the universe around you remains serene, silent, and utterly at peace with itself. Light itself is one of the universe's most beautiful mysteries. The starlight touching your eyes right now has traveled across space at exactly 186,282 miles per second, the cosmic speed limit, the fastest anything can travel. This isn't just the speed of light through empty space. It's a fundamental property of the universe itself, woven into the very fabric of reality. Nothing with mass can ever reach this speed, and nothing can exceed it. Light moves at this precise velocity because that's the speed at which causality itself propagates through spacetime. What makes this even more remarkable is that light doesn't experience time the way you do. From a photon's perspective, if it could have a perspective, no time passes during its journey. A photon leaving a star 1,000 light-years away and arriving at your eye right now experiences both its emission and its absorption as the same instant. The entire 1,000-year journey, from our perspective, happens in zero time from the photon's point of view. It exists in a timeless state, connecting distant moments in space as if they were one. This means that when you see starlight, you're witnessing a kind of temporal bridge. That photon links the star as it was years ago with your eye as it is right now, collapsing centuries into a single moment of perception. You're not just seeing across space, you're seeing across time, your eye receiving messages from the past, your present moment touching the distant past of stars through this strange, timeless messenger called light. Light is both a wave and a particle, exhibiting properties of both depending on how you observe it. This dual nature, called wave-particle duality, is one of the strangest confirmed facts about reality. When not being observed, light behaves like a wave, spreading out, interfering with itself, creating patterns of brightness and darkness. But when it interacts with matter, when it's absorbed by your eye or detected by an instrument, it behaves like a particle, a discrete packet of energy called a photon, delivering its message in one quantum jump. The light from different stars arrives in different colors, carrying different amounts of energy. Blue light has more energy than red light, its waves oscillate more rapidly, its photons pack more punch. This is why hot stars appear blue and cooler stars appear red. When you look at the subtle colors in the night sky, you're not just seeing aesthetic variation, you're reading an energy spectrum, a temperature gauge written in electromagnetic radiation, information encoded in the frequency of light waves. But visible light is just one small slice of a much broader electromagnetic spectrum. The stars are also emitting radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays, all the same fundamental thing, electromagnetic radiation, just at different frequencies. Your eyes evolved to see the narrow band of wavelengths that our sun emits most strongly, the frequencies that penetrate Earth's atmosphere most effectively. It's no coincidence that the light you can see matches the light that's most available and most useful for survival on Earth's surface. If you could see in infrared, the night sky would look entirely different. Cool objects invisible to your eyes would glow warmly. If you could see in ultraviolet, hot stars would blaze even more brilliantly. If you could see in radio waves, the sky would be filled with signals from pulsars, galaxies, and exotic cosmic phenomena and invisible light. The universe is broadcasting in all these frequencies simultaneously, you're just tuned to receive one narrow band, like a radio locked to a single station while countless others play unheard. The atmosphere itself filters much of this radiation, protecting you from the harmful ultraviolet light, X-rays, and gamma rays that would make the surface of Earth uninhabitable. The ozone layer absorbs most UV radiation. The entire atmosphere blocks X-rays and gamma rays almost completely. You're living at the bottom of a protective ocean of air that lets through just enough light to see by while filtering out the frequencies that would harm you. It's another gift, another way the universe has arranged itself to make your existence possible. When starlight enters your eye, it passes through the cornea and lens, which focus it onto the retina at the back of your eye. There, specialized cells called rods and cones absorb the photons, triggering chemical reactions that generate electrical signals sent to your brain. The photon that traveled for years or centuries across space ends its journey by changing the configuration of a single molecule in your retina, a protein called rhodopsin, which initiates a cascade of events that ultimately results in your perception of a point of light. Your eyes are astonishingly sensitive. Under ideal conditions, In complete darkness after your eyes have fully adapted, you can detect as few as a handful of photons. Some studies suggest that individual rod cells in your retina can respond to single photons, though your brain requires several photons arriving close together in time before it registers the signal as light. You're a photon detector, evolved over hundreds of millions of years to be exquisitely sensitive to these tiny packets of electromagnetic energy. The pupil of your eye dilates in darkness, opening wider to gather as much light as possible. This adaptation takes time, about 20 to 30 minutes for your eyes to reach maximum sensitivity. This is why astronomers use red lights to preserve their night vision. Red light doesn't trigger the chemical changes in your rods that white light does, allowing your eyes to remain dark adapted even when you need to see what you're doing. If you want to see the faintest stars tonight, give yourself time in darkness, let your pupils expand, let the rhodopsin in your rods regenerate, let your visual system adjust to the low light levels. Ancient astronomers, before the invention of telescopes or cameras, relied entirely on their dark-adapted eyes. They spent hours in darkness, charting the positions of stars and planets with remarkable precision, creating star catalogs and astronomical tables that remained useful for centuries. They understood that patience was rewarded, that the longer you spent in darkness, the more the sky revealed itself. Modern light pollution has robbed many people of this experience, but the capability remains in your eyes, waiting to be used if you give it the chance. The light you see has wave-like properties that create some beautiful phenomena. When light from a distant star passes through Earth's atmosphere, it can be refracted, bent, by atmospheric moisture, creating halos around bright stars or the moon. Sometimes ice crystals high in the atmosphere act like tiny prisms, creating sundogs or lunar halos, rings of light surrounding bright objects. The wave nature of light, interacting with the particulate nature of our atmosphere, creates these optical gifts. Starlight can also be polarized, its waves aligned in particular directions, by scattering or reflection. The blue light you see in the daytime sky is actually polarized sunlight, scattered by air molecules in a way that aligns the light waves. Some animals, like bees, can detect this polarization and use it for navigation. You can't see it directly, but with polarized sunglasses, you can detect some of these effects, evidence of light's wave nature expressing itself in subtle ways. Every photon carries information about the temperature of the star that emitted it, about the elements present in that star's atmosphere, about the star's motion toward or away from us, about any intervening material it passed through on its journey. Astronomers can decode this information using spectrometers, spreading starlight into its component wavelengths and reading the dark absorption lines where specific elements have removed specific frequencies. It's a cosmic barcode, a signature written in light, allowing us to determine the chemical composition of stars trillions of miles away without ever touching them. So when you see starlight tonight, you're not just seeing pretty points of light. You're receiving information transmitted across space and time, carried by electromagnetic waves traveling at the universe's maximum speed, ending their journey in your eye where they trigger ancient molecular mechanisms that convert photons into perception. You're part of a system billions of years in the making, stars creating light, space transmitting it, eyes receiving it, brains interpreting it, all working together to give you this moment of connection with the cosmos. Let the light wash over you, these ancient photons completing their journeys, these timeless messengers bringing you their silent news from distant suns. Close your eyes when you're ready, and the light will still be there, still arriving, still carrying its eternal information across the void, patiently waiting for the next time you look up to receive it. Imagine, just for a moment, that you could step back and see the universe not as separate objects, stars and planets and galaxies, but as a unified whole, an ocean of matter and energy flowing through space-time. The stars aren't isolated islands, they're currents in this cosmic sea, concentrations of hydrogen and helium slowly burning, converting mass into energy through the patient alchemy of nuclear fusion. Every second, our sun converts about 4 million tons of matter into pure energy. 4 million tons simply ceases to exist as matter, transformed into the light and heat that warm our planet. Following Einstein's famous equation, energy equals mass times the speed of light squared. That conversion factor, the speed of light squared, is so enormous that even tiny amounts of mass release tremendous energy. A single gram of matter, fully converted to energy, would release as much power as 20,000 tons of TNT. And yet, despite converting 4 million tons per second, the sun has been burning steadily for 4.5 billion years and has enough fuel to continue for another 5 billion years or more. Its mass is so vast, 330,000 times the mass of Earth, that this seemingly enormous loss barely affects it. The sun is patient, generous, converting its substance into warmth and light in a controlled reaction that has remained stable for longer than you can truly comprehend, reliable as clockwork, gentle as a candle flame despite the nuclear furnace at its core. Deep in the sun's core, where temperatures reach 15 million degrees Celsius and pressure is immense beyond imagination, hydrogen nuclei are forced together to form helium. Each fusion reaction releases a tiny amount of energy in the form of a gamma-ray photon, an extremely high-energy form of light. But that photon doesn't immediately escape the sun. Instead, it begins a long, random journey outward, bouncing from atom to atom, being absorbed and re-emitted countless times, gradually losing energy with each interaction. This journey from the sun's core to its surface takes somewhere between 10,000 and 170,000 years, depending on the photon's path. It wanders through the dense interior like a drunk person walking home, taking 2 steps forward and 1 step to the side, billions upon billions of collisions before finally reaching the surface and escaping into space. So when sunlight touches your skin, that energy was generated tens of thousands of years ago in the sun's core, only now completing its journey to the surface and then across the 93 million miles to Earth in just 8 minutes. The stars you see at night are all doing the same thing, converting mass to energy, burning through their hydrogen fuel, radiating light and heat into the void. Some are more profligate than our sun, massive blue giants that burn so hot and bright they'll exhaust their fuel in just a few million years. Others are miserly red dwarfs, so cool and dim they can burn for trillions of years, far longer than the current age of the universe. Each star finds its own balance between gravity trying to crush it and fusion pressure pushing outward, a dynamic equilibrium that can last for incomprehensible spans of time. This balance is delicate but stable. If fusion produces too much energy, the star expands slightly, which reduces the core density and temperature, which slows the fusion rate. If fusion slows, gravity compresses the core, which increases density and temperature, which speeds up fusion. It's a self-regulating system, a thermostat built into the very physics of stellar structure, ensuring that stars burn steadily rather than exploding immediately or sputtering out. The universe has arranged matter and energy in such a way that stability emerges naturally from the laws of physics. When stars finally exhaust their hydrogen fuel, their fate depends on their mass. Stars like our sun will swell into red giants, their outer layers expanding to enormous sizes while their cores contract and heat up. The Sun will eventually engulf Mercury and Venus, and possibly Earth as well, though by then it will have lost so much mass that Earth might drift outward and escape. But whether Earth survives or not, it will be sterilized by heat, its oceans boiled away, its atmosphere stripped, returning to the lifeless rock it was before water and air and life transformed it. After the red giant phase, stars like the Sun gently puff off their outer layers, creating those planetary nebulae we spoke of earlier, leaving behind a dense core called a white dwarf. This remnant is incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth, and incredibly hot, glowing white-hot from residual thermal energy. But with no more fusion to generate new heat, it simply radiates this stored energy into space, gradually cooling over billions upon billions of years, eventually becoming a black dwarf, a cold, dark cinder floating through space, the final resting state of stars like our Sun. More massive stars have more dramatic endings. When they exhaust their fuel, they can no longer support themselves against gravity's crush. The core collapses catastrophically in less than a second, releasing so much gravitational energy that it triggers a supernova explosion, the entire star detonating, releasing as much energy in a few weeks as our Sun will emit over its entire 10 billion-year lifetime. For a brief time, a single supernova can outshine an entire galaxy of hundreds of billions of stars. These explosions are violent, destructive, terrifying, and absolutely essential to the existence of complex matter in the universe. Remember, the Big Bang created only hydrogen, helium, and trace amounts of lithium. Every other element, the carbon in your body, the oxygen you breathe, the iron in your blood, the calcium in your bones, the gold in jewelry, the silicon in sand, was created inside stars and dispersed into space by stellar winds or supernova explosions. You exist because stars died, because they converted their substance into heavier elements and returned those elements to the interstellar medium where they could be incorporated into new generations of stars and planets. You are not just made of stardust, you are made of supernova debris, the ash of stellar explosions mixed with the dust of gentler stellar deaths, all of it gathered together by gravity 4.5 billion years ago to form the Sun and its family of planets, including the one you rest upon now. The atoms in your left hand probably came from different stars than the atoms in your right hand, each with its own history, its own journey through space and time before finding its way into the molecular structures that make you alive, make you conscious, make you capable of looking up and wondering about your origins. The heaviest elements in your body, elements like gold and uranium, weren't even created in ordinary supernovae. They required even more extreme conditions, the collision of neutron stars, the densest objects in the universe apart from black holes. When two neutron stars spiral together and merge, they create conditions so extreme that rapid nuclear reactions can build up elements heavier than iron, scattering them into space in a kilonova explosion. The gold in any jewelry you own was created in such a collision, probably billions of years ago, scattered into space, incorporated into the cloud that became our solar system, condensed into the planet Earth, brought to the surface by geological processes, mined, refined, and shaped into its current form. Every element tells a story of cosmic alchemy, of matter being transformed under extreme conditions, of the universe exploring all the possible ways that protons, neutrons, and electrons can combine. There are 118 elements we know of, from hydrogen with 1 proton to oganesson with 118, each one a different arrangement of fundamental particles, each one created under specific conditions somewhere in the universe's history. And here's something wonderful, the elements in your body are not permanently yours. You're constantly exchanging atoms with your environment. You breathe in oxygen created by plants, which used energy from sunlight to split water molecules. You exhale carbon dioxide, returning carbon to the atmosphere. You eat food, breaking down complex molecules and rearranging their atoms into the structures your body needs. You shed skin cells, lose hair, excrete waste, all processes that return atoms to the environment. Within about 7 years, most of the atoms in your body will have been replaced by different atoms. You're not a fixed collection of matter, you're a pattern, a dynamic process, a temporary arrangement of atoms that maintains its structure while constantly exchanging material with the world around you. You're like a wave on the ocean, maintaining your form while the water that constitutes you constantly flows through and is replaced. The universe is breathing through you, cycling its matter through this particular pattern that temporarily calls itself by your name. So rest in this knowledge: you are the universe experiencing itself, matter arranged in such a way that it has become conscious, capable of contemplating its own origins and nature. The atoms that form you have existed for billions of years, cycling through stars and planets and living things, and they'll continue existing for billions of years after you, taking new forms, participating in new stories, forever part of the cosmic ocean that flows through space-time. You are ancient and temporary, unique and universal, both infinitesimally small and profoundly connected to everything that exists. Let that paradox comfort you as you drift towards sleep beneath the stars that made you possible. Claude is AI and can make mistakes. Please double-check responses. Not all stars shine with constant, steady light. Some pulse and vary, growing brighter and dimmer in regular rhythms, like cosmic heartbeats marking time across the galaxy. These are the variable stars, and they've taught us some of the most important lessons about the universe's true scale and nature. One of the most beautiful types are the Cepheid variables, stars that rhythmically swell and shrink, brightening and dimming with periods ranging from a few days to several months. As the star expands, it cools slightly and dims. As it contracts, it heats up and brightens. This happens with clockwork regularity, the same period repeating over and over, a cosmic pendulum swinging through cycles of light and darkness with perfect consistency. In the early 1900s, an astronomer named Henrietta Swan Leavitt discovered something remarkable about these Cepheid variables. She noticed that the brighter a Cepheid's average luminosity, the longer its period of variation. A Cepheid that pulses once every 10 days is intrinsically brighter than one that pulses once every 3 days. This relationship is so precise, so reliable, that once you measure a Cepheid's period, you know exactly how bright it truly is. And if you know how bright something truly is, and you can measure how bright it appears from Earth, you can calculate its distance. It's simple geometry: a candle appears dimmer the farther away it is, and if you know the candle's actual brightness, you can work backward from its apparent brightness to determine how far away it must be. Cepheid variables became standard candles, cosmic distance markers that allowed us to measure the true scale of the universe for the first time. Using Cepheids, astronomers discovered that many of the fuzzy nebulae visible through telescopes were actually entire galaxies far beyond our own Milky Way, island universes separated from us by millions of light-years of empty space. The universe suddenly became vastly larger than anyone had imagined. What seemed like a cozy cosmos with everything contained within our galaxy exploded into an almost incomprehensibly vast expanse filled with billions of other galaxies, each containing billions of stars. Other variable stars pulse for different reasons. Our Lyrae variables are older, smaller stars that pulse with periods of less than a day, useful for measuring distances to star clusters within our own galaxy. Long-period variables like Mira take months or even years to complete a cycle, some varying so dramatically they can change from visible to invisible to the naked eye over the course of their cycle. Then there are the eclipsing binaries, pairs of stars orbiting so close together and aligned in such a way that, from our perspective, they regularly pass in front of each other. When the dimmer star passes in front of the brighter one, the system's total light drops. When the brighter star eclipses the dimmer one, the drop is less pronounced. By carefully measuring these eclipses, astronomers can determine the star's sizes, masses, and orbital characteristics, learning intimate details about stellar systems hundreds of light-years away just by watching their light vary over time. Algol, the demon star in the constellation Perseus, is one of the most famous eclipsing binaries. Its name comes from Arabic, meaning the ghoul or the demon, because ancient astronomers noticed its strange behavior. It would maintain constant brightness for about 2.5 days, then suddenly dim for several hours before returning to full brightness. They didn't know why, and the inexplicable variation seemed ominous, supernatural. Now we understand it perfectly. Algol is actually two stars, one bright and one dim, orbiting each other every 2.87 days, and when the dimmer star passes in front of the brighter one, we see the temporary dimming that so mystified ancient skywatchers. Some stars vary irregularly, unpredictably, their brightness changing in response to stellar weather, massive convection currents, enormous magnetic loops, giant star spots like sunspots but thousands of times larger. These stars remind us that stellar surfaces are dynamic places, not perfectly smooth spheres but roiling, churning, active environments where plasma rises and falls, where magnetic fields tangle and snap, where the physics of extreme temperatures and densities creates phenomena we're still working to fully understand. And then there are the cataclysmic variables, binary systems where one star is actively feeding material to its companion. When a normal star orbits close to a white dwarf, the white dwarf's intense gravity can pull gas from the normal star's outer layers. This gas spirals inward, forming an accretion disk around the white dwarf, heating up through friction until it glows brilliantly. Periodically, when enough gas accumulates on the white dwarf's surface, it can trigger a thermonuclear explosion, a nova, causing the system to suddenly brighten by factors of thousands or even millions, creating what appears to be a new star in the sky. The word nova comes from the Latin for new, because ancient astronomers, seeing a star suddenly appear where none had been visible before, thought they were witnessing stellar birth. Now we know novae aren't new stars at all, they're old stars in tight binary systems, experiencing explosive episodes that can repeat every few decades or centuries. The star isn't being created, it's just temporarily much brighter, announcing its presence to the galaxy before fading back to its normal, dimmer state. Even our own sun is technically a variable star, though its variations are very small, less than 0.1% over its 11-year activity cycle. As sunspots come and go, as the sun's magnetic field flips and reorganizes itself, the total energy output changes slightly. These tiny variations are enough to influence Earth's climate subtly, though not enough to cause the dramatic climate changes we're currently experiencing. Those have other causes. But it's a reminder that even the most stable-seeming stars are dynamic, changing, responsive to internal processes that play out on timescales from seconds to centuries. Some of the most extreme variables are the red supergiants near the end of their lives. Betelgeuse, which we mentioned earlier, varies irregularly over periods of months and years, sometimes dimming dramatically. In late 2019 and early 2020, it dimmed so much that astronomers wondered if it might be about to explode as a supernova. It turned out the dimming was probably caused by a massive dust cloud ejected from the star's surface, temporarily blocking our view, but the episode reminded everyone that Betelgeuse is indeed approaching the end of its life and could explode at any time, tomorrow or 100,000 years from now. When it does explode, it will be spectacular. For weeks or months, Betelgeuse will shine as brightly as the full moon, visible even in daylight, casting shadows at night. It will be the astronomical event of a millennium, visible to every human on Earth, a dramatic reminder that the universe is dynamic and that even the seemingly eternal stars have finite lifetimes. And yet, when it happens, the explosion itself will have occurred 650 years earlier. We'll just be seeing the light finally reaching us after its long journey through space. There's something peaceful about these stellar rhythms, these pulses and variations. The universe has heartbeats measured in days and weeks and years, rhythms you can observe if you're patient enough, patterns emerging from the laws of physics playing out in stellar interiors and binary orbits. Some of these cycles have been repeating for millions of years, will continue for millions more, cosmic clocks ticking away in the darkness, keeping time according to schedules set by gravity and nuclear physics and the structure of spacetime itself. Tonight, several variable stars are visible in the sky above you, pulsing through their cycles, some brightening, some dimming, each following its own internal rhythm. Most of the time you wouldn't notice their variations without careful measurement, but they're there nonetheless, subtle changes in brightness painting the sky with temporal patterns invisible to casual observation but real and measurable and meaningful to anyone patient enough to watch and record and understand. Let these cosmic heartbeats comfort you. The universe has rhythms, cycles, patterns that repeat with reassuring regularity. Stars pulse, planets orbit, moons circle, galaxies rotate, everything moving according to laws that have remained constant since the beginning of time. You're resting in a universe that, despite its vastness and strangeness, operates according to comprehensible principles, creating order out of chaos, structure out of randomness, beauty out of simple physical law. The stars are keeping time for you, their pulses marking the passage of cosmic hours and days, their light varying in patterns you can predict and understand. Sleep peacefully beneath these celestial timepieces, these ancient clocks that have been counting out their rhythms since before Earth existed and will continue long after, patient and persistent and perfectly regular in their endless cosmic dance. There's something we often forget to appreciate about the night sky, the darkness itself. We focus on the stars, the moon, the planets, all the sources of light, but the darkness between them is just as important, just as worthy of wonder. Without darkness, there would be no stars to see. Without darkness, the universe would be fundamentally different, perhaps impossible. This darkness has a name in astronomy. It's called Olber's paradox, though it's not really a paradox once you understand it. The question is simple: if the universe is infinite and filled with stars, why isn't the night sky blazingly bright? Every line of sight should eventually intersect a star's surface, filling the entire sky with stellar brilliance, making night as bright as day. And yet, it's dark. Beautifully, peacefully dark. The answer lies in the universe's age and its expansion. The universe is not infinitely old, it's about 13.8 billion years old. Light has only had that long to travel through space, which means we can only see stars and galaxies within a sphere about 13.8 billion light-years in radius. Beyond that distance, light simply hasn't had time to reach us yet. The universe might extend infinitely beyond what we can see, but we're limited by the cosmic horizon created by light's finite speed and the universe's finite age. Additionally, the universe is expanding, carrying distant galaxies away from us. The most distant galaxies are receding so fast that their light is stretched to longer and longer wavelengths, shifting from visible light to infrared to microwaves to radio waves, becoming invisible to our eyes. The expansion itself dims the universe, creating darkness where there might otherwise be light. So the darkness you see is an absence, it's a message. It tells you that the universe has an age, that light travels at a finite speed, that space-time itself is expanding. The darkness is cosmological data, information about the fundamental nature of reality written in the absence of light. You're looking at the edge of the observable universe, at the limits of what can be seen, at a horizon beyond which lies mystery. This darkness is also essential for life. If the night sky were bright, if starlight filled every direction with blinding brilliance, Earth's temperature would be completely different. The delicate balance of day and night, the cycle of heating and cooling that drives weather patterns and makes complex ecosystems possible, requires darkness. Night allows the Earth to radiate heat into space, cooling after the day's solar heating, creating temperature gradients that move air and water and energy around the planet. Without night, without darkness, plants couldn't follow their circadian rhythms, the daily cycles of opening and closing, photosynthesizing and resting, that optimize their growth. Animals couldn't sleep, couldn't rest their metabolisms, couldn't recover from the day's activities. The very concept of time would be different. We mark time by the alternation of light and dark, by the rhythm of day following night following day, a pulse so fundamental that it's built into our biology at the cellular level. Your body knows darkness. Your pineal gland responds to the absence of light by producing melatonin, a hormone that makes you sleepy, that tells your body it's time to rest and repair. Right now, as you lie in darkness, your melatonin levels are rising, your body temperature is dropping slightly, your heart rate is slowing, all natural responses to darkness, ancient mechanisms inherited from ancestors who lived and died by the rhythm of day and night. Darkness is also where dreams happen. In the darkness of sleep, your mind processes the day's experiences, consolidates memories, makes connections between disparate ideas, sometimes producing those strange, surreal narratives we call dreams. Darkness gives your conscious mind permission to rest while your unconscious mind works, sorting and filing and making sense of everything you've experienced. The night is when your brain does its housekeeping, preparing you for another day of consciousness. Even the darkness of space serves a purpose. It insulates us from the radiation of distant stars, allows us to see cosmic structures clearly, creates the contrast necessary for observation and understanding. If space were filled with a glowing medium, we'd never see individual stars or galaxies, everything would blur together into undifferentiated brightness. The emptiness, the vacuum, the darkness, these aren't deficiencies. They're features that make the universe comprehensible and beautiful. Ancient peoples understood darkness differently than we do today. Before artificial lighting, before cities that glow all night, darkness was complete and absolute. The night sky was far more visible, far more present in daily life. People navigated by the stars, told time by the constellations, used the moon's phases to organize their calendars. The sky wasn't just something you glanced at occasionally, it was an essential tool, a constant companion, a source of wonder that was impossible to ignore. The Milky Way would have been visible on most clear nights, a glowing river of light stretching across the entire sky, so bright it cast subtle shadows, so prominent that every culture created myths to explain it. The darkness made the light more precious, more noticeable, more meaningful. When you can't simply flip a switch to banish darkness, you develop a different relationship with both light and shadow, appreciating each for what it offers. Today, most of humanity lives under light-polluted skies. In cities, The night sky is washed out by streetlights and buildings and advertising, making it difficult or impossible to see any but the brightest stars. Many people have never seen the Milky Way with their own eyes, have never experienced the profound darkness that reveals the sky's full glory. This is a loss, a disconnection from something fundamental to human experience, a severing of the ancient relationship between people and the cosmos. But darkness still exists, waiting patiently for anyone willing to seek it out. If you travel away from city lights, if you give your eyes time to adjust, if you allow yourself to sit in darkness without immediately reaching for a light switch or a phone screen, the sky gradually reveals itself. First the brightest stars appear, then dimmer ones, then more and more until you're surrounded by thousands of points of light, the Milky Way stretching overhead like a cosmic river, the universe presenting itself in its full, overwhelming glory. That darkness is a kind of silence, visual silence, the absence of light pollution allowing the subtle signals from distant stars to reach your eyes. Just as silence allows you to hear quiet sounds, darkness allows you to see dim lights. The two senses operate similarly, both requiring absence, emptiness, lack of interference in order to detect subtle signals from far away. And there's something deeply restful about darkness. It removes visual stimulation, gives your eyes permission to close, allows your visual cortex to stop processing information and enter a more relaxed state. Darkness tells your entire nervous system that it's safe to power down, to stop vigilantly scanning for threats, to enter the vulnerable state of sleep. Without darkness, true rest becomes difficult or impossible. So tonight, appreciate the darkness as much as the light. Notice how the black sky makes the stars visible, how the shadow creates contrast, how the absence defines the presence. The darkness isn't empty, it's full of possibility, full of rest, full of the quiet that allows both the universe and your own mind to reveal their deeper patterns. Let the darkness embrace you like a soft blanket, wrapping around you, protecting you, giving you permission to release the day's concerns and drift into sleep. The stars will keep watch while you rest, their ancient light crossing the darkness to stand vigil over your dreams. The universe has arranged itself so that darkness and light alternate, ensuring that both work and rest, activity and recovery, stimulation and peace all have their designated times. You're safe in this darkness, held by gravity to the surface of a planet, protected by an atmosphere, warmed by residual heat from the day's sunshine, covered perhaps by actual blankets, surrounded by the infinite gentleness of the night. The darkness is not your enemy, it's your oldest friend, the condition that makes rest possible, the canvas on which the stars paint their light, the peaceful void that allows you to close your eyes and let go of consciousness for a while. Sleep now, held by darkness, watched over by starlight, cradled by a universe that provides both light and shadow in perfect balance, both activity and rest in endless rotation, both questions and mystery in harmonious proportion. The night is here for you, patient and gentle, waiting to receive you into its soft, dark embrace. The night sky you see tonight is both unique and eternal. This exact configuration of stars and planets will never appear again. The moon is in a specific phase, at a specific point in its orbit. The planets have moved to positions they won't occupy again for years or decades. Even the stars have shifted imperceptibly in their slow drift through the galaxy. This moment is singular, unrepeatable, yours alone to witness. And yet, the patterns repeat. The constellations return season after season, year after year, century after century. Orion rises in the winter, just as it did for the ancient Egyptians, for the builders of Stonehenge, for every human who has ever watched the winter sky. The Big Dipper circles the North Pole tonight just as it will tomorrow night and every night after, patient and eternal in its rotation. The cosmos operates in cycles, daily, monthly, yearly, cosmic, each one a reminder that despite constant change, there are also deep continuities, reliable patterns, things you can count on. The Earth completes its rotation every 24 hours, bringing you from daylight through twilight into night and back to dawn again. This rhythm has continued for over 4 billion years, slowing gradually but maintaining its essential pattern, spin, 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 an endless turning that creates the succession of days that mark your life. You've experienced thousands of these rotations already, and there will be thousands more, each one slightly different in detail but identical in structure: light, darkness, light again. The moon cycles through its phases every 29.5 days, waxing from invisible new moon to brilliant full moon and back to darkness again. 13 of these lunar months roughly equal one solar year, which is why many ancient calendars were lunar, tracking time by the moon's reliable transformations. Women's menstrual cycles evolved to approximately match the lunar cycle, another connection between earthly life and cosmic rhythms, bodies responding to ancient patterns, biology synchronized with astronomy. The Earth orbits the Sun once per year, creating the seasons as our tilted axis alternately presents each hemisphere toward or away from the Sun's direct rays. Spring follows winter follows autumn follows summer in endless succession, the same sequence repeating year after year, creating the framework within which life organizes itself. Plants bloom in spring, fruit in summer, seed in autumn, rest in winter. Animals breed, raise young, prepare for scarcity, endure cold. Everything alive follows these cycles, these cosmic cues, these reliable patterns established by orbital mechanics. The planets themselves follow longer cycles. Jupiter takes about 12 years to orbit the Sun, spending roughly 1 year in each zodiac constellation, slowly making its way around the ecliptic. Saturn takes nearly 30 years for one complete orbit. If you saw Saturn in a particular constellation as a child, you might have to wait until middle age to see it return to that same position. These slower rhythms create longer patterns, cycles within cycles, wheels within wheels, the solar system operating like an enormously complex clock with gears that mesh at different rates. The Sun has its own cycles too. Every 11 years, its magnetic field flips, north becomes south, south becomes north, and the number of sunspots rises and falls in rhythm with this magnetic cycle. During solar maximum, the Sun is dotted with dark sunspots, active regions where intense magnetic fields inhibit convection and create cooler patches on the surface. During solar minimum, the Sun is often spotless for days or weeks at a time, its surface relatively calm and uniform. These solar cycles affect Earth subtly. More sunspots mean more solar flares and coronal mass ejections, which can trigger auroras at high latitudes, beautiful curtains of green and red light shimmering in the northern and southern skies. The solar wind, a stream of charged particles flowing outward from the Sun, interacts with Earth's magnetic field, channeling particles toward the poles where they collide with atmospheric molecules, exciting them and causing them to glow. The aurora is Earth's atmosphere responding to the Sun's magnetic weather, creating light shows that dance across the polar night. Even the stars themselves, seemingly fixed in their positions, are slowly moving through space, each following its own orbit around the galactic center. The Sun completes one galactic orbit every 225 to 250 million years, a period sometimes called a cosmic year. In the time since dinosaurs first appeared on Earth, we've completed less than one full orbit around the galaxy. The last time the Sun was in its current position relative to the galactic center, the continents were arranged differently, the climate was different, the dominant life forms were different. But from our perspective, these changes are imperceptible. The stars appear fixed because they're so far away that their motion, thousands of miles per hour in many cases, creates almost no apparent change in position over human lifetimes. The constellations our great-great-grandparents saw are the same ones we see, and our great-great-grandchildren will see them too. The cosmic year is so long that human civilization, all of recorded history, is just a brief moment within it. There are longer cycles still. The Earth's axis wobbles slowly, a motion called precession that takes about 26,000 years to complete one cycle. This means the north celestial pole traces a slow circle through the stars, with different stars taking turns as the pole star over millennia. Right now, Polaris happens to be near the pole. It's our North Star, our navigational anchor. But 5,000 years ago, Thuban and Draco was the pole star, and 13,000 years from now, Vega will have that honor. This precession also means the dates when the Sun enters each zodiac constellation slowly shift over time. The astrological signs used in horoscopes were established over 2,000 years ago, and due to precession, they no longer match the actual positions of constellations. When astrologers say the Sun is in Aries, astronomically it's actually in Pisces. The sky has shifted, but the astrological system hasn't updated, creating a disconnect between the traditional names and astronomical reality. Ice ages come and go on Earth in cycles roughly 100,000 years long, driven partly by variations in Earth's orbit, sometimes more circular, sometimes more elliptical, and by wobbles in the tilt of Earth's axis. These Milankovitch cycles, named after the Serbian scientist who worked out their mathematics, show how even Earth's orbit isn't perfectly stable but varies slightly over tens of thousands of years, creating climate variations that have shaped the evolution of life. And beyond all these cycles lies the universe's own evolution. The universe began in the Big Bang 13.8 billion years ago, and it's been expanding ever since, growing cooler and less dense as space itself stretches. Galaxies are moving apart from each other, carried by the expansion of space, creating a cosmos that looks different at different cosmic epochs. The night sky you see tonight is darker than it was billions of years ago, when galaxies were closer together and the average distance between stars was less. Eventually, trillions of years from now, the expansion will carry distant galaxies beyond our cosmic horizon. Their light will be stretched to such long wavelengths, and they'll be receding so fast, that they'll become completely invisible. Future astronomers, living in that distant era, will see a night sky containing only their local galaxy group. Everything else will have receded beyond observation. They won't be able to discover the Big Bang or the expansion of the universe through observation, because all the evidence will have literally moved beyond their ability to detect it. But that's so far in the future it's almost meaningless to consider. Tonight, the sky is rich with galaxies and stars, patterns and cycles, rhythms you can observe and understand. Tonight, you're living in a cosmic epoch where the universe reveals its history and structure to anyone patient enough to look and think and measure. You're privileged to exist at a time when the night sky still tells stories, still offers evidence, still provides connection to the deep past and distant reaches of space. All these cycles, daily, monthly, yearly, cosmic, create a universe that is both changing and stable, both dynamic and predictable. Nothing is truly permanent, But many things are reliable enough that you can count on them, plan by them, orient your life around them. The sun will rise tomorrow. The moon will wax and wane. The seasons will turn. The stars will wheel overhead in their ancient patterns. This reliability is a gift. In a universe governed by entropy, where everything tends toward disorder and randomness, these cycles persist, these patterns repeat, these structures maintain themselves generation after generation. They provide a framework, a scaffolding of predictability within which life can flourish and consciousness can develop, and you can rest peacefully, knowing that the fundamental rhythms will continue, that tomorrow will come, that the cosmos will still be here when you wake. So let yourself be held by these cycles, these eternal returns, these patient rhythms that have continued since long before you existed and will continue long after. You're part of something vast and ancient and reliable, a universe that knows how to maintain itself, how to persist, how to create order out of chaos and pattern out of randomness. The same forces that keep planets in orbit are keeping you safe, the same laws that make stars shine are making your existence possible. Rest now in the embrace of cosmic time, knowing you're cradled by forces and patterns larger than yourself, more enduring than any worry or concern. The universe will turn, the earth will spin, the stars will rise and set, all without your conscious effort, all while you sleep and dream and recover your strength for another day. Trust the cycles. Trust the patterns. Trust the eternal return of light and darkness, warmth and coolness, waking and sleeping. The night is here to hold you, the cosmos is here to contain you, and the cycles are here to reassure you that despite all the changes and chances of life, there are deep continuities, reliable patterns, things that endure. Close your eyes now and let yourself drift, carried by Earth's rotation toward tomorrow's dawn, held by rhythms older than time, wrapped in the gentle certainty that the universe knows what it's doing and will carry you safely through the night. As you rest beneath the stars tonight, you're not alone in your observation of the cosmos. All across the planet, others are looking up too, amateur astronomers peering through telescopes, lovers sharing quiet moments under the moon, children making wishes on stars, elders remembering a lifetime of nights beneath this same sky. Right now, at this very moment, countless eyes are raised upward, each person finding their own meaning, their own comfort, their own connection to the infinite above. And it's not just humans. Animals experience the night sky too, though in ways we can barely imagine. Nocturnal creatures emerge as darkness falls, navigating by starlight that seems dim to us but provides enough illumination for eyes evolved to gather every available photon. Owls hunt beneath the stars, their exceptional night vision allowing them to spot tiny movements in near total darkness. Moths navigate using the moon as a compass, maintaining a constant angle to that distant light source as they fly, though this ancient navigation system now confuses them when they encounter artificial lights and spiral helplessly around bulbs and flames. Sea turtles, hatching on beaches, instinctively move toward the brightest horizon, which naturally would be the starlit ocean rather than the dark land, though artificial lights now sometimes lead them astray, drawing them inland instead of toward the sea. Dung beetles navigate using the Milky Way, the only insect known to orient itself by the galactic plane, using that broad band of light to roll their precious spheres in straight lines across the African savanna. Even these tiny creatures are astronomers in their own way, their nervous systems attuned to celestial patterns, their behavior shaped by the same sky you're watching now. Migratory birds fly thousands of miles guided partly by the stars. They can detect the Earth's magnetic field, yes, but many species also use the rotation of stars around the celestial pole to determine which direction is north. Young birds, on their first migration, must learn the star patterns during the weeks before their journey, imprinting the sky's rotation into their memories, carrying that celestial map with them as they fly across continents and oceans. Seals and whales navigate vast oceanic distances, and while much of their wayfinding relies on other senses, echolocation, magnetic sensitivity, ocean currents, some species may use celestial cues as well, surfacing to observe the sun's position by day or stars and moon by night. The night sky is a universal reference system, available to any creature with eyes capable of seeing it, a shared resource that life on Earth has been using for hundreds of millions of years. Even plants respond to celestial rhythms. The moon's phases influence plant growth in subtle ways, and many plants have circadian clocks synchronized to the day-night cycle, opening flowers in response to sunlight, closing them at night, their biology entrained to the rotation of the Earth just as yours is. Some plants even track the sun's motion across the sky, their leaves or flowers slowly turning to follow the light. Heliotropism, sun following, a botanical form of astronomical observation. These plants, these animals, these other observers of the night, they're your companions in this moment, sharing the same sky, responding to the same celestial cues. All of you inhabitants of a planet wrapped in darkness half the time, all of you adapted to make use of whatever light reaches you. You're part of an ancient community of stargazers, a lineage stretching back hundreds of millions of years to the first creatures that developed light-sensitive cells and began responding to the difference between day and night. Your own eyes are evolutionary marvels, the product of countless generations of refinement. The rods in your retina, those cells specialized for night vision, are so sensitive they can detect single photons under ideal conditions. They contain a protein called rhodopsin, visual purple, which changes shape when struck by light, triggering a cascade of chemical reactions that amplify the signal until it's strong enough to send an electrical impulse to your brain. This system is so efficient that if it were any more sensitive, you'd see the random thermal fluctuations in your own eye as phantom flashes of light, visual noise that would obscure actual signals. The fact that you can see stars at all, that you can detect these impossibly distant points of light, is remarkable. A star 1,000 light-years away emits photons in all directions, and an infinitesimally small fraction of them happen to travel in exactly the right direction to enter Earth's atmosphere, pass through the air without being absorbed or scattered, enter your pupil, be focused by your lens, and strike a rod cell in your retina. The odds of any particular photon making this journey are astronomically small, and yet enough photons complete the journey that you perceive the star as a point of light. Every photon that reaches your eye has won a cosmic lottery, surviving a journey across space and time to deliver its message. And your eye is ready to receive it, a biological detector refined over hundreds of millions of years of evolution, optimized to extract maximum information from minimum light, allowing you to navigate and hunt and appreciate beauty even in near darkness. But you're not just a passive receiver of starlight. You're also emitting radiation, infrared radiation, the heat from your body radiating outward into the night. Right now, you're glowing in the infrared spectrum, invisible to your eyes but detectable by thermal cameras or by snakes with heat-sensing pit organs. You're a warm beacon in the cool night, radiating energy that was originally sunlight, captured by plants, eaten by you or by animals you ate, metabolized in your cells, and now being released as heat that flows outward from your skin into the surrounding air and eventually into space. This radiation you're emitting will travel outward forever, at the speed of light, gradually diluting but never disappearing. Some tiny fraction of your thermal radiation will escape Earth's atmosphere and begin a journey through space, perhaps eventually reaching distant star systems billions of years from now, carrying the faint signature of your body's warmth across the cosmos. You're contributing to the universe's energy budget in your own small way, participating in the cosmic flow of energy from hot to cold, from concentrated to dispersed, from order to entropy. The Earth itself is also radiating heat into space, the accumulated warmth from sunlight, from radioactive decay in its core, from the residual heat of its formation. This thermal radiation is essential. Without it, Earth would continuously heat up until it became uninhabitable. The balance between incoming solar energy and outgoing thermal radiation determines Earth's temperature, creating the narrow range of conditions where water remains liquid and life can flourish. Right now, as you lie beneath the stars, you're part of this energy flow, absorbing radiation from your surroundings, emitting radiation from your body, maintaining your temperature through the constant exchange of heat with the environment. You're a thermodynamic system, temporarily maintaining order and complexity by consuming energy and radiating waste heat, fighting against entropy locally while contributing to it globally, alive because you can sustain this delicate balance. And all around you, unseen, are other forms of radiation passing through your body. Cosmic rays, high-energy particles from deep space, are constantly striking Earth's atmosphere, creating cascades of secondary particles that rain down on the surface. Right now, several cosmic rays per second are passing through your body, most of them doing no damage, just ghosting through as if you weren't there. Some of these particles began their journey in supernova explosions millions of light years away, accelerated to nearly the speed of light, and after traveling for millions of years, they happen to pass through your body at this particular moment. Neutrinos, ghost particles that barely interact with matter at all, are passing through you in incomprehensible numbers, trillions per second, mostly from the sun but some from distant supernovae and other cosmic sources. They pass through the Earth itself as if it weren't there, traveling at nearly the speed of light, unaffected by gravity or electromagnetism, barely existing in the physical world at all despite their vast numbers. You're transparent to neutrinos, as is everything else. They're all around you, through you, constantly, invisibly, connecting you to nuclear reactions in the sun's core and in distant dying stars. Even the light you can see is passing through you in a sense. When starlight strikes your body, some is reflected, some is absorbed and converted to heat, but the photons don't pass through. Your body is opaque to visible light, which is why you cast a shadow. But radio waves pass right through you, as do X-rays and gamma rays, in small numbers, thankfully, making you transparent to large swaths of the electromagnetic spectrum even as you're opaque to the narrow band your eyes can detect. So you're simultaneously isolated and connected, solid and permeable, alone and accompanied. The night wraps around you like a blanket, but it's a blanket woven from radiation and particles, energies and fields, all flowing through and around you constantly, connecting you to the sun and stars and the deep structure of space itself. You're immersed in the cosmos, bathed in its emanations, participating in exchanges of energy and information that link you to everything that exists. Other humans, other animals, other living things, they're all experiencing this same immersion, all connected to the same cosmic web of energy and matter. The photons that miss your eye strike the ground, or a tree, or another person. The heat you radiate warms the air around you, mixing with heat from other sources, creating subtle currents and flows. The neutrinos that pass through you also pass through everyone and everything else, democratic and indiscriminate, touching all things equally. You share this night with all of life on Earth, all of you turning together on the planet's surface, experiencing darkness together, waiting together for dawn. You're part of a global community of conscious beings, each aware in your own way, each experiencing this moment of existence, each held by the same gravity, warmed by the same distant star, sheltered by the same thin atmosphere. And beyond Earth, there might be others, on worlds orbiting distant stars, looking up at their own night skies, seeing different constellations, different patterns, but experiencing the same fundamental wonder at the cosmos that contains them. We don't know if they exist, these possible others, but the universe is so vast and contains so many stars and planets that it seems unlikely we're alone. Somewhere, Perhaps, another consciousness is looking up right now, contemplating the same questions, feeling the same mixture of smallness and connection that you feel when you truly see the night sky. Whether those others exist or not, you're not alone beneath the stars tonight. You're accompanied by all of life, by the long history of consciousness emerging from matter, by every human who has ever looked up and wondered, by the very cosmos itself which, through you, has become aware of its own existence. Rest in that companionship, that connection, that participation in something larger than yourself. You're held by invisible forces, connected by imperceptible flows of energy, accompanied by unseen companions both earthly and cosmic. The night is full of presence, full of relationship, full of the quiet communion between all things that exist beneath the same sky, governed by the same laws, participating in the same great unfolding of reality. Let yourself feel held by this invisible web of connection as you drift towards sleep, knowing you're part of something vast and ancient and ongoing, accompanied always, never truly alone, cradled in the embrace of a universe that contains multitudes.